to correct its valve position so that subsequent increment to the fuel will occur or not. So in this speed governor operation, speed changer is the first point. I can adjust the required input fuel to the turbine directly from set point itself or along with the speed governor. So this speed governor is an option. Suppose if I say a numerical problem, there is no speed governor operation. Then this action feedback is not there. Whatever the set point you set, that set point is directly making a subsequent opening up of the valve, and opening up of the valve ensures certain flow to the turbine and ensure your frequency, and it is not going to have feedback. That's called only speed changer controlling the required output to the turbine, means fuel to the turbine. Suppose you are inclined to see to that drop in the RPM, drop in the frequency you would like to correct. Then it becomes necessary to incorporate feedback network. This becomes a feedback network. Speed governor, when included to the system, whatever is the set point, according to the actual feedback, what the RPM is possessed right now, is going to transform the reference point into another displacement called as a power displacement by this network. So as we were discussing earlier, this fly ball mechanism having the two rotating balls rotating in a vertical plane. So this is vertical from the point B. Assume that there is a vertical falling down mechanism to which you have rotating input. So this fly ball mechanism keep rotating continuously, and the speed input to this rotating mechanism is very high. Definitely whirl effect makes this black circled dots, nothing but fly balls go away centrifugally. Then this arm B point is pulled downward. Then when the speed of this governor mechanism, our actual RPM is very slow, definitely this spring mechanism contracts towards center and this mechanism is pulled upward. B point is pulled upward. It means to say set point is shifted by this feedback network mechanically from the actual speed of the turbine according to the shift what is obtained on the P reference proportional to the speed what it is exactly possessing will have a displacement in position. Those displacement will permit the hydraulic oil to enter inside the chamber and make the subsequent corrections to close the valve or open the valve as per your requirement. That was what we have seen. When I say governor free means this network is not there. That you have to understand. With the governor means set point and governor together functioning to control your requirement. So that's what the basic we need to remember for today's understanding. Then we took a simple example in the earlier closing session. A 100 megawatt 50 hertz generator is connected to infinite network. How would you increase its turbine power by 5 megawatt? It means when I say infinite bus concept, if you remember back, there is a terminal for exchange of power in the grid where there is a huge generator connected to which enormous capacity available with which it is able to deliver active and reactive power, keeping the frequency constant and the terminal voltage constant. That is a standard reference we identify as infinite nature. Suppose your system is infinite network. To such a infinite network, one of the generator is connected to deliver the power in parallel to that. Then how is that 5 megawatt extra power you need to increase from this generator to get in connection with the finite network? Then what is to be done? It is directly this turbine power can be increased by 5 megawatt by simply giving rise signal 5 megawatt to the speed changer motor. Why this is exactly? It is not being seen. So when I say infinite, frequency deviations are 0. When it is synchronized to an infinite bus, when I say infinite, frequency deviation is 0. When frequency deviation is 0, definitely I will not have any feedback from the actual sensor here. So whatever is the sensing you do here, setting you do, that setting will directly go to this point to open or to close the valve. It means the demand is increase the mechanical power by 5 megawatt As the generator is connected to infinite bus, the speed deviation, frequency deviation at a finite bus is 0. You do not have any deviation in the frequency. Hence, you will not get the corrections required from the feedback network to shift this point upward. What it was rotating, it will be continuously rotating at the same speed. It is not having any fall in speed or raise in speed. Hence, point B will not shift C up or down. Hence, whatever the displacement you are expecting as a supplement to the mechanical input to the turbine, you have to control from the speed changer only. When I say infinite bus being interfaced with the generator set point need to be changed. It is because feedback network will not provide any feedback to us. That is the meaning of this. So turbine power can be increased by 5 megawatts, whatever the increment said, simply by giving rise signal of 5 megawatt to the speed changer motor only. This is because the frequency deviation is 0. The turbine power nothing but the reference point shipment only. How do you get it? The frequency deviation is 0 at infinite network. Now if I go back, how you get it? Let us say this equation. This equation we have the governor, what the displacement it is going to give is nothing but the reference point what it is having and the deviation from the feedback divided by droop characteristics of that. So the same thing is done over here also. Delta PG, incremental, minute change in power displacement required, delta PG from the governor's perspective is delta P reference, whatever is that change expected here, minus 1 divided by R into delta F or delta F by R, where delta F is called frequency deviation noticed as a line frequency. So that deviation is 0 in case of infinite network. Therefore, you will get delta PG equal to delta PREF. Nothing but delta PG itself is not there, governor is not in operation, then it comes back to reference only. So that's what is the meaning over here. Turbine incremental power required when generator is connected to infinite network, it is the reference point shifting only. If generator is connected to finite network where there is a contingent change in load, like a real-time power system integration, where there is a load change, there is a fall of frequency, then there is a need to correct the frequency and input to the turbine. That's what we have to see. This is called ideal case. When it is an ideal case, whatever is the incremental power you would like to demand, that is a change in set point. It may be other way also. When you are in the infinite network, you decided to decrease on a certain generator 5 megawatt power less. You want to decrease it. Then what you should do? Give a lower command, fall command of whatever the megawatt you want to that motor. It means speed governing, speed changing motor. It is directly what you request as a speed changer will be implemented at the turbine. That's the meaning of infinite bus integration. Next, suppose it is a finite, but I say real-time power system. So consider this network as a finite, its frequency is variable. That's the meaning. When I say finite, frequency is variable. So we do, however, keep the speed changer at constant setting, that is delta P ref equal to 0. It means the equation, whatever the equation we were referring to this context, it is delta PG equal to delta P ref delta F by R. This change, whatever the setting you have done and not at all changing. You are not, once you set it, left off. That's called P reference is set. Delta P ref is called incremental change. You should be very careful. P ref is set point. Delta P ref is incremental change expected. Minute either upward shift or downward shift. We call it as delta P ref. So that's what the meaning I am trying to convey here. So delta P reference is 0. I am not changing it. Whatever the setting I have done, it is done locked. No more changing of this. That is the delta P ref is 0. Then we have a infinitesimally small change in turbine power. PT0 turbine power output is equal to delta P ref 0 minus delta F divided by R. This is the equation how that power balance is done. This is the feedback. This is the feedback from the turbine with the droop nature, delta F initial divided by droop nature and set point. This mismatch is the requirement of the delta P0. The turbine has to either accelerate or decelerate such an action which is to be at the turbine. When we have finite network, turbine need to compensate that required drop in frequency or RPM. Suitable supplement need to be demanded. What is that supplement? That supplement, what we are speaking is delta PT, infinitesimally small shift in power demanded by the turbine for a certain operation is with the P reference 0, constant setting. You are not modifying the P reference. P reference is set and locked. It is then only delta F divided by R. The turbine has to adjust according to the speed deviation divided by droop nature is the correction required. It means the above equation, this equation shows that for a constant speed changer, as the speed changer is not at all altered repeatedly, it is kept set and stop. Then constant speed setting, the static increase in turbine power, whatever the contingent increment or decrement of turbine power due to change in load, that's the nature, which I said static increase in turbine power output is directly proportional to the static frequency droop or drop. Whatever is the drop happened, that much is the correction you should apply at the turbine. It means valve have to operate corresponding to the drop in frequency. It is just like an automobile driving concept. The speed setting is done at 60 km per hour. P reference is 60 km per hour. Then possibly there is no correction required for 60 km per hour. Whatever the driver has to pedal it so that the RPM which is fallen down to reach 60 km per hour, he has to pedal the accelerator such that is the range he has to reach by that. Delta F0 is the actual deviation. Delta PT0 is the pedaling what he has to exercise against the set point 60 km per hour like that. It means you are not tampering it. Set 60 km per hour, that particular set point, you are adhering. 0 to 60 km per hour is your pedaling option. You pedal it from 0 to highest, then incremental change in the RPM or speed you will get on the vehicle. Similarly, when the P reference at the speed setting point is 0, not changing it, and whatever is the fall in RPM or frequency you notice, that is the delta F0 divided by R correction required for the turbine to compensate that speed drop. That's the meaning. The constant speeds in the setting, static increase or decrease of output of turbine is proportional to the frequency only. From this we can write above equation, delta F0 is equal to the shift required into droop value. We can see droop is mentioned by the governor for the particular generator, 4%, 5%, like that droop is mentioned. So deviation you need to calculate. This means that plot of frequency with respect to power, if it is a straight line with a slope of R, droop characteristics. So this shows when it is connected to finite network, it is natural that there is a fall in RPM or fall in frequency. The turbine need to cope up that by having incremental opening up of valve adopted. So when it is a finite, it is the droop comes into picture. Proportional to the frequency deviation, droop will play and opening up of valve to supplement required mechanical power to the turbine so that this drop is arrested or this drop is worked out by the turbine. Incremental power addition to that. So that is how we have to do. Let's see one more option. If the governor is there, it will do by this correction. If there is no governor, this is called impact of governor-free operation and frequency drop. Let us say this is very important to understand this problem. You will see in the numerical section of your exam question paper or understanding, a text will be quoted like this way. A two generator concept. Two generators, 250 megawatt and 400 megawatt are operating in parallel. In a station, it is a scenario. The droop characteristics are 4% and 6% respectively. How a load of 600 megawatt is shared among them is the question. What will be the system frequency when they are sharing 600 megawatt, when both are being in parallel with the characteristics of 4% and 6% droops? What will be the new frequency? And assume that 60 hertz is the standard required frequency. And later there is a notice, no governor action. It means what? There is no network which will correct your frequency fall. It is to understand, if there is no governor, what will be the effect of that load on the generator such that fall in frequency which is noticed, which is tremendously increasing. So let us see how to understand this problem. So when we have a droop characteristic, it is a plot of frequency and power. So you can see a red line, one simple line is drawn to show you how the droop of a certain generator, 1 pu power, highest capacity of power, when it is delivering, it is at base frequency f0, something like that. So it is a nominal frequency is f0, able to deliver full capacity at that time. Suppose you want to draw 50% of that, it is definitely nominal frequencies more than that, somewhere it will intersect here. So this is how a nominal curve of any droop relevancy is drawn, frequency and power. It may be omega and power. So it is the droop nature. So I have two generators with me, 250 megawatt and 400 megawatt. Let us have a similarity, droop number 1, droop number 2. I have just drawn two curves. Then I assume that, let us say f0 is a frequency which I intersect with these two lines. Basically they are operating at certain point which is developing a power P1 megawatt, and at f0 it is developing a power P2. It means 250 megawatt and 400 megawatt generator operating in parallel. Let us say initially they were at frequency f0, correspond to something which you will connect it to one another. Base frequency somewhere f0. This is intersecting this blue line somewhere here. Power output available at that time was say P1 megawatt from machine number 1. And similar f0 line intersecting on this curve projected downward show you P2. P1 plus P2 show me initial share, let us say. Or you can just say at 0. Even you can say when I come down to 0 axis here, at initially 0 load on that, this was the frequency prevailing. And 0 load on that, this was the frequency prevailing on that. Whatever is that. Initial power P1, P2, f0 is the frequency. As the load increases on them, suppose 600, definitely as the load increases, if I move along the x-axis over here, if I move away, definitely as I come down along this line, when I have certain power point here, just a stop point and project backward with the frequency. Frequency is definitely less than what it was operating. As the load increases, it is natural to have drop in frequency I am trying to convey. So whether it is a 600 megawatt or whatever the megawatt, as the load increases, naturally along this curve, the point of shift is noticed. Let us say P1 is shifted to P1 dash, certain point. Then similarly for this machine, P2 is the intersecting point with the F0. Due to some loading, it has shifted downward. Let us say 600 megawatt is shared by these two generators. Then 600 megawatt, how it is shared up by 250 watt megawatt? What is the portion shared by 400 megawatt? I have to calculate. To calculate that, let us imagine this graph which are drawn. Let us say P1 dash and P2 dash are the new operating points. New operating points intersecting with a certain frequency, which is f dash, wherein the shift from P1 to P1 dash is called delta P1. What is the extra power? It should cope up. And from P2 to P2 dash, what is that additional power generator 2 has to generate such that they together, delta P1 plus delta P2 together become 600. That is the scenario. So what I am doing now, when I have delta P1 plus delta P2, surely their operating frequency f0 has come down to f dash. It is reduced frequency than nominal frequency. The question comes here. When I say governor free operation, the drop in frequency is not compensated. You are supposed to calculate and understand loading phenomena. If the load occurs, How is that frequency falls? And it initiates for governor's operation. Now, when there is no governor-free operation, let us study what is that shift downward, what is that frequency from base expected fallen down and where it will stand. Let us say, let the load shared by unit 1 be X megawatt. I am just making a simple scenario. And another is 600 minus X. Simple relationships. XB by unit 1 and 600 minus X megawatt by second generator. Then I assume, let us say, the decrement in frequency, we call it as delta F, frequency deviation. New frequency and base frequency. When I take a difference, this is called delta F. I wrote here. Let the reduction in frequency be delta F. We have a relationship. The frequency deviation noticed by these two generators in parallel, say delta F divided by X, the share of first machine, is equal to, look into this, how equations are written. Delta F divided by share of X, first machine, is equal to first machine droop nature. What is the droop nature? 4%, 0.04, 4% into the frequency. What is the frequency of the system? 60. So R into droop into frequency divided by capacity of first machine. I repeat back, this relationship is transformed into understanding of what is that frequency deviation experienced by these two machines in dealing 600 megawatt. I am trying to correlate by mathematical terms. That is done by delta F divided by X from the first machine's perspective is equal to, what is delta F? 4% of 60. That's called 4% of 60. 0.04 into 60 divided by the capacity of first machine, 250. This is first relationship. Similarly, I have second machine relationship. What is second machine? Delta F divided by sharing of second machine, 600 minus X, is equal to its relationship. Its droop is 6%. 0.06 into 60 hertz divided by capacity of that. So these two are the basic equation I can correlate when I have governor-free operation very easily. Then I will solve these two equations. How I did? Delta F by X from the first machine, its droop into frequency divided by its highest capacity. Second machine, droop delta F divided by sharing 600 minus X equal to droop into frequency divided by its capacity. I divide equation 1 divided by equation 2. If I take delta F by X, you can see, divided by this term, delta F by 600 minus X. I am dividing this equation 1 by equation 2. You can imagine, equal to this term divided by right hand side of this term. I put it in the term. First equation divided by second equation. Here delta F is common, cancelled out. When I solve this, what I will get here now? This X comes to the denominator, 600 minus X goes to the numerator. And this right hand side, this term, 0.04 into 60 divided by 250 into inverse ratio of this, which is 400 divided by 0.06 into 60 will be a term here. If I cancel the numerical values, reduce them, I am able to get what is X from that. So on solving, by taking the ratio of these two, reducing it to get the value of X, X stands to with the value 290.42 megawatt. 290.42 megawatt. And what is that? 600 minus X then. 600 minus X stands 309.58. If I add these two, it should become 600 for me. This is how proportion to their capacity. You can see 290 is smaller, 309 is larger. So sharing of power takes place in proportion to capacity and characteristics of the machine. This was one of the equations we have learned. I go back and show you. This is what we have seen. Delta P1 by delta P2 equal to R2 by R1. The delta P1, delta P2 were the incremental changes here. This is a change, this is a change. So in proportion to their capacity and droops, there is a relation. So this is what is being taken over here. So therefore, when I solve this equation, X is nothing but 290.42 shared portion of the load of 600 by 250 megawatt. It means it's an increment. Don't worry about that. Why this is how come 250 can be shared by this one? This is to show you what is expected on this. Then other is 600 minus X, 309.58. So this is how this machine has to share 309. So together it should work for me 600. Now using this, the second is what will be the system frequency when there is no governor action. There is no action of governor to control the input to the turbine. But what will be the change in frequency noticed? Is it an acceptable frequency or not? We would like to know it. That is to initiate turbine governor operation. Then I take either first equation or second equation. In that I substitute X value. You can see here I took the first equation. Delta F by X equal to 0.04 into 60 divided by 250. On substituting X value, I will be getting value of delta F. Delta F stand as 2.788 Hertz. It means there is a dip of 2.788 Hertz from the nominal frequency 60 Hertz. It is, let's imagine, F0 was the base frequency, these two were working. When suddenly due to demand of extra 600 megawatt, the line, operating point along this droop, operating point on this droop fallen down, because of which there is a dip in frequency noticed. The dip was 2.788 Hertz. Then what is the actual frequency on the scale then? It is F0 minus delta F. If I say it is 60 minus 2.788 stand as 57.21 Hertz. This is how when there is no governor operation, naturally frequency falls. The fallen frequency subjected to your criteria, acceptable or not acceptable? Definitely it is not acceptable. It is to show you whenever there is a numerical problem, when there is a keyword no governor action or governor free mode of operation, how we should work? By ratio of deviation to the sharing, you should compare, you should solve the share and get the value of particular deviation. This is how you have to work, very straightforward when there is no governor. But similarly, I have some other problem solved by different authors. How they work, we will see. This is a very simple problem. Proportion to their capacity and characteristics, there is a sharing. When there is no governor action, frequency drop is noticed. If it is a governor-based operation, this drop was adjusted and controlled by governor itself by subsequent shift in megawatt supplement by the turbine's power, it would have been adjusted. We will see in the next upcoming slide how it is being worked out. This is to show you the basic working of governor-free operation. Now, let's see one more problem there. An example of 100 megawatt 50 hertz generator. In the previous example, the first one which you have seen, it has a regulation of 4%. And by how much will the turbine power increase if the frequency drop by 0.1 hertz with a speed changer unchanged? Now, there is a demand. This problem is posing you a question. Here, turbine droop nature of 4% will adjust the fuel so that turbine is going to shift its output for every drop of frequency in the line. How much power is really a deficit noticed? Because of that, drop in the frequency in the system is observed, is to be understood. I repeat back. Considering a 100 megawatt 50 hertz generator in the example, the droop nature of the turbine and governor associated with which was 4%. By how much will the turbine power to be increased? Increment in power is required. For a drop of 0.1 hertz, frequency in the system. Then without changing the set point, how is that adjustment being done? I go back to the screen and I'll try to convey you. Let's come to this point. Speed changer, this point is not at all modified. There is no adjustment here. It is a fixed point, set and fixed. And turbine is getting a power from this valve position. This particular valve position has made the turbine to drive the generator, and frequency at the generator has fallen down 0.1 Hertz. 0.1 Hertz is the drop in frequency. Now, this governor is getting a feedback of the RPM, which is having 4% droop nature. How is that? This governor going to act on the set point, which is fixed. No more there is a change of delta P. It is a fixed point, and this governor is going to reflect the drop in RPM or the frequency with its droop of R%, such that that shift will be brought to this hydraulic amplifier and valve being just opened, so that higher fuel will rush. That higher fuel will address drop in RPM. That drop in RPM will improve the frequency back to zero, error back to zero. So I am trying to focus. If this governor is in action for a constant setting, how this is going to modulate the A with C. A is shifted to C with the B point. B is operating on D. D is making a valve movement, pilot valve movement. Oil is making the displacement, and piston is going to either open or close according to the decision of the B. Therefore, I am in need of calculation of what is that correction this governor is going to do for the turbine to increase or decrease power. In this case, increase of power. This has to cause opening up of valve. That's what the meaning of me. So just I'll come back here. Okay, this was the point. So there is a drop of 0.1 Hertz. Then how I will understand regulation of 4%? Whatever the percent means 4% of its base frequency. Base frequency is 50 Hertz in this case. So 4% of 50 refers to 52 Hertz or 2 Hertz. So for the base frequency 50, 52 is a point. 52 down to 100 megawatt. What is its capacity? 100 megawatt. It is expected to deliver 100 megawatt at 50 Hertz. Then the 4% droop means 4% of 50 in RPM. What I get here? That is the base frequency plus that. That's called 50 plus 2, 52. You have to draw graphically a line with 52 Hertz point with 100. X-axis is the power scale. Y-axis is the frequency scale. So certain point which you will connect it to a point of 100 megawatt. Therefore, this horizontal line is now as a base line. Base frequency of what? 50 Hertz. That is your reference point. The horizontal reference is 50 Hertz. The natural droop of 4% makes it 52 Hertz. From 52 to a point of 100, draw a line. This slope of this is 4%. This is the meaning of that. Slope of this line is 4%. Now, it means frequency drop off. You can see here, the 4% of 50 Hertz means 2 Hertz. This means frequency drop of 2 Hertz. The turbine power will increase by 100% of the capacity, means 100 megawatt. Therefore, it's R. How is that R correcting the input fuel? R is delta F. What is delta F? Divided by its capacity. Delta F by delta P means P. 2 divided by 100. It is going to make 0.02 Hertz per megawatt. It means there is a drop of 2 Hertz means, or for every 2 Hertz change, 100 megawatt is compelled. Now for me, what is the compelled drop? Not 2 Hertz. It is only 0.1 Hertz. For 0.1 Hertz, what is that correction I have to do? I have to calculate. To calculate that, I have to calculate effect of regulation. Regulation is for 2, that is 2 Hertz divided by capacity. So much of 0.02 hertz per megawatt is the shift it is going to do. Then what is noticed in the problem is delta F is 0.1 hertz. This is the 0.1 hertz. Now I will not worry about this minus. Minus is nothing but a drop for me. So I'll just worry about numerical content. Delta F is 0.1 hertz. I know that because of load there is a drop. So this minus indicates drop for me. So delta F is 0.1 hertz. Now I know from the turbine governor mechanism, turbine's power required is P reference minus 1 divided by R into delta F. It means when it is connected to an example, constant setting, speed changer is not going to change. Delta P ref is 0. Delta P ref is 0. Therefore, the subsequent change expected by the turbine is delta F divided by R with a sign. Then I can do it as the value of delta PT equal to delta F 0.1 divided by 0.02. So there is a natural minus and minus cancels away. It means it is 0.1 hertz delta F divided by R. R stand here as the value of hertz per megawatt. 0.02 hertz per megawatt. When I operate in the denominator, it becomes 0.1 divided by 0.02. Subsequent minus and minus cancel away. It is demanding 5 megawatts. See here, when this particular generator is connected to a grid and experiencing a 0.1 hertz drop in the frequency, it means this 0.1 hertz is because of deficit of 5 megawatt at the line side. It means there is a demand of 5 megawatt which was not addressed momentarily, that has caused a drop of 0.1 hertz. Now to cope up this 0.1 hertz back to error free, making it to 50 hertz only, what the generator should look for? Increment of mechanical power to the turbine. By what value? Minimum 5 megawatt supplement to be taken from the turbine so that RPM improves. When RPM improves, the error of the frequencies settle to 0. That is numerically 5 megawatt. So here comes the role of governor. So if I did not have a governor to play, definitely the frequency which has fallen down 0.1 would mean 50 minus 0.1. It is 49.9. That would be an accepted or accepted one. Whatever is that. When there is a governor action, governor is meant to make the error in the frequency to 0 by subsequent correction in the input fuel of the turbine. So this simple example, a 4% of 50 hertz of a certain function makes your freedom of 2 hertz. For 2 hertz of deviation, it opens 0 to 100% of the capacity. For ratio, when I take hertz per megawatt, what is the drop of minute hertz in per megawatt? Then it becomes 2 divided by 100 its capacity. So much of hertz, if there is a drop per megawatt, it's going to correct 0.02 hertz per megawatt. So every 0.02 hertz drop, 1 megawatt of kind of power is compelled. So therefore, here is a drop of 0.1 hertz. 0.1 hertz with respect to 0.02. I am comparing here. So therefore, shift required in the turbine power is delta F divided by R, which works out 0.1 divided by 0.02 as 5. 5 megawatt is the need of the hour. This is how it should be worked out. So you learned here, or you got to know how these governor based action plots are done. Frequency and power, and what you mean by 4% of base frequency, how to locate it, what is the base frequency, how to begin from that point. This exercise gave you a point. And how to get the droop calculation of that. That's called R equal to deviation, what you get from the calculation of 4% or any X% divided by its capacity. That is the minute hertz per megawatt the governor is going to act on. Then what is your shift required? You have to calculate. So we'll see some more problems. We will be able to cope up this also. This is how a basic need of governor is operated. Here governor free frequency drop is not corrected. But here a minute 0.1 hertz drop is not acceptable. It is to be corrected. By what? Subsequent power you have to supplement the turbine. This shows that On supplement of 5 megawatt to the turbine, arresting of this 0.1 hertz error is done by the governor. Then, see another problem here. Consider again the similar 100 megawatt 50 hertz generator concept. If the frequency drops by, it's almost a similar one. I can just see a point drops by 0.1 hertz, but the turbine power remain unchanged. See the context here. Turbine power remains unchanged. By how much should the speed changer setting be changed? It means, just see here the problem. 100 megawatt 50 hertz generator concept as usual. System is delivering a load and experienced a drop of 0.1 hertz. Now turbine is not going to manipulate the requirement. Then what is that set point changing I should do to correct this? Here governor is not in the play. Governor is not correcting the turbine power. Then who has to correct this 0.1 hertz? It is the speed changer. I go back and take you to the screen here. This is what I am speaking. Here there is a drop of 0.1 hertz in the line. Turbine has decelerated. Here this turbine will not take a correction from the governor. Governor will not act on the input control. Then you want to address this 0.1 hertz drop. Then who can work on this? Only the speed changer. Either I can compensate it if it is physically acting. If this is not acting for the case, how to address that drop of 0.1 hertz? I have to come from speed set point. Manually I have to increase the generation here. So that increase in generation, A will get shifted to C without the action of B, and C will be on D. Shiftment will make it to open. It means a governor's action is not there. Turbine is not going to correct through the governor. It is going to get corrected through the set point change only. Set point change will directly make the valve to open and close. This open and close can be either by set point or by the governor mechanism or by the movement of this block itself. These are the 3 points of this movement. This movement is connected to hydraulic block, connected to a governor which can moderate the position, or it can shift it by this way. 3, 1, 2, 3. There are 3 points of action which will definitely make the position controlled. Now this control is not there. Then who can work for this drop then? Only the speed changer. That is the question being posed here. This one. Considering the same 100 megawatt 50 hertz generator, the frequency drop is again 0.1 hertz. Turbine power remain unchanged. It means the governor is not going to manipulate the output of the turbine. It is not going to take care of the power. What should be the correction at the speed changer? Initial set point. What should be done then? It is to calculate the similar one using this turbine power is equal to delta P reference minus delta F by R. So here we can say turbine power is not going to take any correction, only the reference point and these are in connection. So when this becomes 0, when turbine power is not going to supplement for this changes by governor action, no shift here, only shift is from reference set point. Reference set point and these two, if I transfer one on other side, 0 equal to P reference minus 1 by R into delta F. So P reference has to be proportionally controlled to deviation. It means already we know it. So it is R equal to 0.02 hertz per megawatt. In the previous example, we got it here. 4% of 50 is 2. 2 divided by 100 is 0.02 hertz per megawatt. 0.02 hertz per megawatt. And delta F naught said is 0.1 drop in the frequency. Then P reference point shift required is delta F by R. Nothing but 0.1 divided by 0.02. 0.1 divided by 0.02. When I take a ratio, it leaves me again 5 megawatt. What it indicates now? Turbine is not going to control it from governor, but command from the reference point make the turbine to adjust. It means to say P reference is shifted by what megawatt? 5 megawatt. So therefore, you should see to that by the line which we had here. We had a basic delivery, a dip in line has occurred, and who has to correct it? It has to be corrected by the governor, not the governor, the speed changer only. No matter 5 megawatt is the answer. We got 5 megawatt here also. But this 5 megawatt was worked out by turbine governor mechanism. But now governor mechanism is not playing a role. Who will play the role to arrest this 0.1 hertz error? It is the initial set point of the system only. So this is to highlight you how correction to the drop in frequency being done by governor, that is the feedback network, and the turbine, and the speed set point which will be riding on the feedback if to be adjusted for your requirement. So this example again make you confident that if there is a subsequent loading on the generating area, the drop in frequency is sure, and controlling of that back to zero error means delta F to zero is necessary. It initiates the governor's action. Then I have one more case study. How you actually work it out. Now let's see a generator. Imagine a generator running in a system. Let us say it is having a certain droop. Droop is some percentage. Let's say in this case I have here. In a case, both the speed changer setting, frequency in which that is called delta PT, the incremental command required by the turbine is equal to reference set point minus the deviation divided by droop nature of the system. This is called power equation. Applies for both the set points. It means, just see this curve there. Suppose this is the frequency scale, this is the power scale. Now the frequency is not mentioned in hertz. Earlier what was in hertz, or it may be in per unit also. Here it is in percentage. 100% refers to its base frequency, like example 50. You can see 50 when I refer is 100%. Here become 100, 101, 102, 103 like that, and below it is 98, 96 like that. So frequency scale is maintained in percentage. This is what is this. Frequency is in percentage. So 50 hertz may be a working frequency. At that 50 hertz, let's see this line. The solid line you observe, 100. 100% of the power of the generator you are taking out, which is followed by 104 connecting to 100. It means 104 refers to 100 plus 4. It is called 4% droop line. So 4% droop line connecting it to 100 output, nothing but the megawatt of a certain generator, 100 megawatt. It is in megawatt scale. So therefore, 100% your 100% of its output you are taking from certain 104 point you join this. This is called 100% rated power at nominal frequency 100%. Say it is a 50 hertz. At 50 hertz, what is the output you are extracting from this generator is its fullest capacity. Let's say 100 example. Suppose you observe a dotted line here. This line, when there is a drop in or increase in load or sharing is changed, it is developing 50% of that. This dotted line, just the horizontal line, this is a line intersecting with the horizontal line with a dotted pattern. You can see this. It is touching this line at 50, 40, 60 at some point, midpoint. It means speed changer set to give rated frequency at 50% of the output power. It means it is working with a 102 to 50 connecting point. The same generator which is having a droop nature working at 50% of its capacity throwing out, and it is interacting with this line. It means suppose it is drawing 60% of the output. This dotted line would touch 60 point. It should touch 80. It should touch 20 like this way. This line parallel to this, there will be several lines parallel to this will appear in the operational aspect of the generator. It means this will show you how the frequency and output of a generator will be controlled in the power system such that for a unit frequency, unit speed regulation frequency, what is the standardized frequency they are trying to maintain in terms of frequency, in terms of percentage or in terms of PU to operate that. What is that controlling at the speed changer and at the governors should be done. It is seen by this droop curve. So the solid line show you the curve which is interacting with the 100% of the power. Generator is able to deliver 100% of its capacity being in unit frequency, base frequency 100%. The same machine, when I reduce the input, to the set point of the speed set point, if I reduce to 50%, is coming to output delivering at unit speed 50%, like this. So this is called how regulation is being done in the controller. We should see here. The droop remains same. The droop is exactly, this line is parallel. Parallel means what? Droop is R%. Whatever is the R is only. But developing an output of 50% here, developing an output of 100% here. Further loading if you do, this cannot meet. That is how this case shows how proportionately turbine power and reference power and droops are interconnected to one another. If turbine power need to be controlled with the speed changer 0, turbine power is directly proportional to frequency deviation. If turbine is not to adjust itself, it is required to set the speed changer, then speed changer nothing but required power change. This is what is the relationship. A line which is intersecting at 100% is to say speed set point is 100%. So suppose turbine power is 0, then P reference must be 100%. If set point is 50%, then automatically 50% will be coinciding with the line of 50 over here. So this is how a thick line shows corresponding to 100% rated frequency. The output power is also 100%. But the new speed changer setting as shown the dotted line to show you effect of speed changer, which is nothing but I am speaking about this point. This point. It is set 100%. The turbine is not in play. 100% means fullest capacity output, which you can see from turbine. If it is 50%, 50% of the flow control is such that output is 50% when the turbine is not in action. Suppose this is not in action, how this will work? What is this highest control and what is the output? I am trying to correlate by this example. So here speed changer is set to 100% and speed changer is set to 50%. That's what is the suitable changer. So as per our desire control, I can set the speed controller settings. Okay. Now, one more general view. This we have already discussed. Suppose I have two generators in a plant. Let's say the solid lines. You can see the grayish like line, dull line, one, another line here. So they are operating at the frequency FR, at rated frequency, which is intersecting at the black dot, and here is the black dot. So y-axis is the frequency scale, x-axis is the power scale. So both the machines are sharing a certain power, which is P1 0, P2 0. So total P1 0 plus P2 0 is the demand borne by these two generators to be stable. As the load increases, naturally there is a fall in frequency. If there is a fall in frequency, definitely that fall in frequency has to be cope up by these two generators according to their proportion that the regulation and capacities are. Therefore, the solid lines shows how they will change their points. Suppose those generators are commanded such that there is a governor in each machine. Governor dictates that it should not compromise the frequency, but it should change the output of the generator by compensating mechanical input to the turbine. See the curve, how they are interacting with this. This line is shifted downward. Downward means this point is shifted somewhere here, which is coincide with this dot solid line with the P1 dash. P1 dash is the new operating point and P20 to P2 dash is the new operating point at the same frequency. Now we can see the frequency is same, dotted line frequency axis is same, but operating point of 1 is shifted to 1 dash and 2 is shifted to 2 dash. It means to say for the unit speed regulation, governors are commanded such that frequency deviation has to be kept in mind to 0. Then what is that corresponding input increment at each turbines to be taken, like an example of 5 megawatt in this case. Here we had, so the speed here we had, the turbine has to increase 5 megawatt. Turbine 1, turbine 2, like that. Turbine only need to increase. That's the same thing. The turbine increment has to happen by governors. So governor will look forward for turbine to increment the power so that it will shift the megawatt on this axis. This slope will have the value, numerical value over here, numerical value over here are different. So it is shifted. And this along which, where we had a point here, shifted. So P1 dash plus P2 dash numerically larger than P10 plus P20. This is how the load division takes place, keeping the steady frequency deviation. Frequency deviation has to be addressed. This line you have to observe carefully. The frequency axis, which is a horizontal line drawn, is not coming down. Naturally, what would happen when there is a frequency fall? I will show you another equation here. When there is a loading effect, load on 1 is increased, load on 2 is increased. The frequency has reduced down here for the new value of load sharing. New value of load sharing. This is a new frequency f dash. This frequency giving you a delta f. Delta f we do not want. If we do not want means this curve has to go forward. Concentric to this, I have to draw another curve here. Concentric or parallel to this, I have to draw another line here. That's what is the shipment being done here. So parallel to this, shift a line. Parallel to this, shift a line. Economically, you calculate what should be the sharing of power at this time by P1 machine or machine 1. What should be the sharing of machine 2. That's called P1 dash, P2 dash. So at the same speed or same frequency. This is how governors will come. If governors were not there, I am quite sure frequency of this will be different, frequency of this will be different. They cannot be in parallel. Therefore, in parallel operation, when the machines are put in station, therefore a common frequency has to be managed. Their regulations have to be kept in mind. This shows another case study how a governor is in play to manage the mechanical increment input or decrement of input to the turbine for the contingent changes in the load to address deviation of frequency to 0. This is a need. Then similarly, I have one more picture to be discussed with you people. Suppose when you have two generators parallel sharing an active power, they definitely are in play to develop a certain power and meet the requirement. I have put something here PL. PL equal to P1 plus P2. Load is addressed by generator 1 developing P1 megawatt and P2 megawatt. And assume that these two generators have certain droop characteristics as I have marked here. Now you can see something different in my plots. The plots are having per unit representation. X-axis you can see it is in power. P1, P2, P2, which you mentioned here, megawatts, output power. They may be in megawatt, they may be in per unit. So X-axis to Y-axis I shift. Y-axis is omega or frequency in per unit. Whatever the 50 hertz, 50 divided by 50, 1. So 1, 1.02, 1.04, 6, 8, 2, as you see. These were the frequencies put in per unit representation. So you got to know, first example I took in terms of frequency itself, 50, 51, 52 like that. Second, another example I compared you in terms of percentage of frequency, 100%, 102% like that. Now I am showing you in terms of the particular value in per unit. So this way, book to book, the understanding of representation keeps changing. But for your understanding, K. Umar Rao textbook, which we are going to refer for this power system and operation control, referring similar to the one which I am shown on the screen. It is on per unit frequency scale. So 1 PU refers to whatever the frequency system is cooperating, 50 or 60. Whatever the values upper side or lower side fall, They are the respective relative values. So now at unit speed regulation at 1 pu, these two generators are having a curve represented blue and red by color. Machine 1 is having red, machine 2 is having blue. From this curve, as I mentioned you in the first example, you can understand what are the minimum and maximum outputs. So if you observe the red one is almost interacting with a zero output here, which is a speed regulation or its unit speed frequency is 1.05, nothing but 5% droop. So 5% refers to 1.05 touch of line, and its capacity is something touching here. Red line touching the x-axis somewhere at this point, which is called P1 max at 1 pu frequency. So first understand the dimension of this representation. Red line you observe, machine number 1. Machine number 1 is having its point on a y-axis somewhere 1.05. It refers to 100 means 1. 1.05 means 0.5 refers to 5% of droop. This machine is surely having 5% droop, which made you to touch 1.05 point over here, and somewhere at this point on the x-axis touching, I call it as a P1 max, output of the machine 1 maximum. At what frequency? 1 pu frequency line. Hence it is a P1 max at 1 pu frequency, and it's 1.05 is the frequency start point at no load. Similarly, you observe the blue now. Blue is machine 2. Machine 2's curve is touching this y-axis at 1.07. Nothing but 7% is its droop. At no load, its frequency is 1.07 pu. At no load, it is 1.07 pu. Then at its full load, it is 1 pu. It is coming down here, which is max power acceptable we can expect here, which is 1 pu frequency is P2 max. P2 max refers to output maximum from the machine 2 at 1 pu frequency is touching here. Along this line, you have a profile. How the power changes, frequency also changes. So this is how a representation being done. Now let us say when we have their initial mark on the frequency scale. Initially, no load frequency is 1.07 nothing but 7%. 1.05 nothing but 5% droop. When they are connected to the x-axis, P1 max, P2 max respectively. Now, I have one more interesting point here. You can see a horizontal line dotted put on this curve, which intersect at red and blue curves, pointing down P1 and P2. What it indicates? When these two generators are in parallel, suppose say, if these two are in parallel, developing certain output P load, say P1 megawatt, P2 megawatt, what is the frequency these two are operating themselves to deal this P load is understood by drawing a horizontal line on this graphical representation, which the value which the line intersect with the curve 1 drops down with the x-axis P1 megawatt, with the same line intersecting on the blue line P2. If I add P1 plus P2, it becomes a frequency. So graphically, how I can do? I can make a scale or riding point, move this dotted line up or down, such that value of P1, P2 when I add together should become P2. This is called a graphical solution of the problem. I should have slope of curve 1, curve machine 1, machine 2 plotted with this dimension, and what is the load you want to operate by these two, and what is the prevailing frequency you would like to know. Then draw a horizontal line and make the line slider like moving up and down, which will intersect these two curves such that intersecting point value you add both together. That should meet your demand of the system. Then pertaining to that meeting up of P1 plus P2 equal to P load, what is that frequency touched on y-axis? That is the operating frequency of the combination. For example, when P1 and P2 are shared by first and second generator for a demand P load, dotted line is interacting at the vertical axis certain point. That point I computed as load sharing approximately by value P1 plus P2 at 1.015 pu. Suppose it is 50 Hertz. Surely it is able to cope up and maintain more than 50 Hertz. It comes below 1 means there is a drop of frequency. This is how the droop curves with the governor manage this. When the governors are there, governors will automatically correct these things and they will make it to operate. So therefore, I want you all people to consider this slide very carefully because I made so many comments on this page. This is the important notice or important thing you should know when you refer Dr. K. Umarao textbook, how each point and how the respective data on this graph is important to me. So this is how two different curves of different ratio. It need not be different. Red and yellow, blue line may have same slope. Then doesn't matter. And capacity need not be same. Capacity may be same. Capacity need not be same. Whatever is that, the parameter of its boundary 1, boundary 2 and intersecting points. If you are able to understand, you are able to solve the numerical problem. Therefore, when the particular generator 1 and 2 are sharing a load, the frequency prevailing to the particular point of sharing can be worked graphically by raising this dotted line up and down so that such P1, P2 makes your P load. This is one of the important study. Now, with this knowledge, let us move one more problem. Just how graphically things can be worked out. And numerically, I have solved in the footer. What is this? Two parallel synchronous generators. There are two generators in parallel. Total load of 200 megawatt is to be addressed. Capacity of both the machines are 100 and 200 megawatt respectively. Machine 1 is 100 megawatt, machine 2 is 200 megawatt. And both together in parallel share a load of 200 megawatt. Both the machines have a governor droop characteristics R1, R2. 4% only. R1 is also 4%, R2 is also 4% from no load to full load. Find the active power load share of each machine assuming free governor action. So, my friends, please note this, governor free action. There is no governor to correct the frequency drop. What is the frequency prevailing when they are meeting a load of 200? I have to understand. Let us do it and I will convey you. The first problem I took, it has dropped down the frequency to 57.277, something like that. Which was a 60 Hertz requirement, it has dropped to 57. That was going below your base frequency. But this problem is having a very narrow load, 200 megawatt load. See how the base frequency is very closely managed above the 1 pu value. Let us see how it is being done. So, to solve this graphically, again, y-axis, x-axis. X-axis being power scale, y-axis being frequency scale. So, what we will do, we will mark this horizontal line as 1 pu and both the units have 4% droop. 4% droop means 1 is 100% and 4 means 0.04. So, 1.04 is a scale have a touch here. If it's a 2%, 1.02. It is a 5%, 1.05. Like that, along the y-axis, from the x reference point 1 unit speed required, you just scale up and mark a point 1.04. What's the rough scale? 1.04, 1 point. This is to say no load. When the load on the machine is 0, means along the x-axis, power scale is 0 value. Only vertically you will be scaling up 1.04. From this point, along the power axis 0, 10, 50, 100, 200, like that. Power points you can mark incremental. Let us say 0, 100, 200. Equally they are marked 0, 100, 200. Now what I will do, the first machine is having a capacity of 100. Droop is 4%. You recall back the problem which we learned here. This problem. 52 Hertz to 100. So 4% droop. 4% refer 4% of 50. This 52. 50 plus 2. So I am doing on Hertz scale. But here what I am doing? Here I am doing PU scale. Whatever is the 50 or 60, it's 1. And 4% of that, 0.04, 1.04. Like my 52 over there, 1.04 here. And take this point. Join with this capacity of that, 100. I am joining a red line here for machine number 1. Then same for 200 megawatt. From the similar 1.04 mega PU mark, join it to 200. I just draw a blue line. By chance, if it was 5% for machine 2, what I should do? Go up here, 1.05. Mark the 1.05. From there, you join the 200 line. Are you sure? So, if it is a 4%, from the same point, I am drawing one line to 100 megawatt. From the same 4%, 1.04, I am drawing a line to 200 megawatt. Graphically, this I have to understand. Once I am able to understand this, I just come down to the theory knowledge here. Come to the basic knowledge here itself. Let X be the share of unit 1. Then share of unit 2 is 200 minus X, which you have learned. Proportional sharing of units. X be the share of unit 1. 200 minus X is the share of unit 2. Then taking this knowledge, delta F by X equal to droop into units frequency divided by 100, what the capacity, and delta F divided by 200 minus X, sharing of other machine, into droop divided by capacity. So this equation, if I utilize and take a ratio of this, if I solve this, X I get as 66.67 megawatt, and Y I mean the other one, 200 minus X, I get it as 133.33 megawatt. So it means for a machine which is having 100 megawatt and 200 megawatt in combination, machine 1 share 66.67 megawatt and machine 2 share 133.33 megawatt. You can see exactly double the power it is sharing, half of the second it is shared by first one. That is the meaning that in an electrical power system, whenever devices are in parallel, the sharing up of load or disturbance is proportional to their capacity and characteristics. This is a very specific relationship. The machines with a higher capacity respond higher by increment. Machine with a lower capacity respond lower by response. The other way, if there is a fault, the first get affected by badly, the other get by lesser. It means the reflection of the component is proportional to their capacity and characteristics. In this due regard, machine 1 being smaller respond for a change of only 66 megawatt. The other is double that capacity, almost double the value is going to respond. Then this is the solution we know from our earlier example. How this is done by graphically? Graphically it is being marked. See how it is that? 1.04 is the no load, its frequency, droop characteristics. Then 1 PU is its normal operating frequency, and 100 is the output highest power from machine 1, 200 is the highest output from the machine number 2. Let us draw somewhere in between 1.04 and 1, draw a dotted line which will intersect the red line at some point and blue line at some point. It means this is the combined frequency which I am drawn a line horizontal to see to that. Suppose this is the common frequency with that both the machines are operating and delivering 200 megawatt common load. Then what is the sharing of machine 1? I can read from this scale. What is the sharing from machine 2? I can read from this bottom. It means this common frequency intersecting line 1, line 2, slope 1, slope 2 give me X. I say let X be the share of machine 1. Then this width is load minus X. Whatever the load I have, 200 minus X is the share of machine 2. The same analytic what we are doing here is graphically shown here. When this is intersecting with a dotted line, this point, let X be the share. Then another point intersecting to the blue line is load minus X. And this decrement you can see. 1.04 is the no load frequency or droop nature of the machine 1, machine 2 being 4%. This is decreased when there is a load. Let's say it falls down by a value y. Y is a drop in frequency scale, which is a horizontal line which I have drawn. From the no load frequency scale, there is a drop or a dip in frequency by a y value. Then that line is just intersecting with a red line to get x share, with a blue line to get p load minus x share. That's what 200 minus x I am trying to speak. Now my question is how to calculate this. To calculate this graphically, look at the other side. Assuming that x equal to p1 share, machine 1 share. Look into this, 0.04 divided by 100. What this 0.04 refers to, you know? 0.04 refers to droop of machine 1. Whatever is the value, droop of machine 1 divided by its capacity, 100, equal to slope of this curve, y by x. This red line is having a slope, y by x. Can you see? Droop of machine 1, 4%, divided by its capacity, 100, is equal to slope of this line, y by x. This is first equation from machine 1 perspective. From machine 2 perspective, what I can write? Again, it is a 4% droop. Again, 0.04 divided by its capacity. What is the capacity of second machine? 200. So 4%, 0.04 divided by 200 is equal to again this triangle formed by blue line. This is a wider triangle. This is again y divided by p load minus x. Can you see here? 200 minus x. Y divided by 200 minus x. This is called referring to the common triangle on the common line. This line and this line is common, and I can take similarity of triangle relationship. I can write. So on proportion, I can write 0.04 divided by 100 equal to y by x from machine 1 perspective, and what is that? 0.04 divided by 200 equal to y divided by 200 minus x. Then I can take ratio of these two equations. Equation 1, equation 2. Y is common, nothing but to delta f. So delta f by x, delta f by 200 minus x. Are you able to see? This y stand here as delta f for me. So both are same. Methods are same. The terminology is y here. In my notation, delta f I refer. Drop in frequency, change in frequency divided by x, change in frequency divided by 200 minus x equal to its droop divided by capacity, droop divided by capacity. So when I take this, x I am going to get as 66.65, and y I am going, another load I am going to get as 133.35. Now the question is, at what frequency these two machines are surely going to combine and work? Are they going to have a frequency less than 1 pu, or what is that frequency these two will fulfill this requirement? Like my 57.277 in the first problem, is it really going below 1 or is it very safer? I would like to know. This is called omega common or frequency common. That is nothing but y for me. Y is 1.04 minus this value. If I get, I'll be getting this operating frequency, which is 1 and 1.04. Somewhere it is marked here. What is the value of this? This value is I am able to get this if I know the value of y. 1.04 minus the y, I'll get this point. Then what I will do? I use one of the equation. 1.04 divided by 100 equal to y divided by x. X I substitute as 66.65 here. If I solve this, I'll be getting y, the value of y. This value of y is just an incremental value here. This position value. This value, if I subtract from 1.04, 1.04 minus this computed y from this equation or this equation will leave me what is the revised frequency over here, which is a dotted line meeting my x and p load minus x requirement, which is 1.013 3, 4 PU. Suppose one is 50. It's definitely 50 into 1.04. Above 50 Hz. It's very safe. So even though governors are not in action, the current load of 200 megawatt is very well above the frequency expected for the pair. So this is how even a small load can meet. This may not be an accepted case if the load is increasing further. This line which is interacting with this line may come so close to 1 and below 1. Maybe higher load demand may not make this parallel combination successful. In this how another graphical way of solving parallel connected generator share and common operating frequency calculation can be seen. So I repeat back, it's very simple. Group 1 you notice on a per unit scale in this context. 1 being basic frequency, whatever the group percentage you have, 0.04 of that, you point a mark here. From that point, capacities of the generator along the x-axis, you put a dot here. Then join this point with the respective line point. Then you draw the slopes. Then you mark at what particular ratio or at what particular frequency these two will share the load. Let's say x be the share of this. Draw one line. Simply draw one line. Mark it as share of first machine be x, and remaining must be load minus x. And the diminished value of frequency from the zero load means no load frequency 1.04 be a value of something y. Then from the ratio of these triangles I can write the group by capacity of the first machine, group by capacity equal to y by x, slope of this curve, first machine. Similarly, group by capacity of second machine is also equal to y divided by wider length of this side, which is P load minus x. Then I take a ratio of these two to get the value of first value x and another value y. X become share of first machine, load minus x become share of second machine, which is being done here. Then to know at what frequency these two machines are able to develop this 200 megawatt, is it safe or not? Because there is no governor. Governor is not in action. What will be the frequency actually thrown out, which is calculated by 1.04 minus this y. If I substitute, I'll be getting this one. So we can see conclusion here. When governors group characteristics are same, generator share the active power load in proportion to their capacities, which I was speaking. The one which is 100 and one with 200, proportion to their capacity, they have shared. This is what is the observation from this particular example, and frequency is still safer for your operation. So this is how you will get another incremental knowledge for your understanding. When I move with the next case study, this is a textbook example only. I have taken it from Dr. K. Umarov textbook because there are about 4 problems which are from problem 1 to problem 2, problem 2 to problem 3. There is a small incremental change, and once you understand the problems carefully, you are able to work out. So this is a similar problem which I have solved just now. Just now, whatever the discussion we have done here, similar discussion is here in this problem. What is this? Two machines operate in parallel to supply a common load. Now, my friends, you remember whatever I am discussing is with the governor action. So governors are there to see to that there will be a control on that. Frequency, now onwards, whatever the problem I am teaching, frequency will not fall below 1 PU. All will be above 1 PU. It is to say to that safer loading or governors can manage it. So now two machines operate in parallel to supply a load of 400 megawatt. The capacities of machines respectively 200 and 500. Each has a group characteristics of 4. No matter, both are having a 4% to me. It is easier for us. Their governors are adjusted so that frequency is 100% on full load. Governors are managing to keep the frequency 100%. Whatever the PU what they want, 50 or 60. calculate the load supplied by each unit and the frequency at this load. Now, for the 400 megawatt load, when is that or how is that sharing of 400 takes place by first machine and second machine? At what frequency they are able to meet this 400 megawatt load? This is what is the question. Unit and frequency at this load. Consider the system frequency as 50 Hertz. It means you have two machines, 200 megawatt, 500 megawatt. Load on the system is 400. System frequency is 50, and governors adjust the requirement with a group of 4% and calculate share and frequency new value. For this, again, look to the graph directly without watching this. Just look to the graph. What is this graph? This graph shows plot of frequency and output power. See here, Dr. K. Umarao Madam represented the frequencies in terms of per unit and power values in terms of per unit. For that, what she has done? 200 divided by 100, 500 divided by 100, considering 100 as a base power. It is being done. 2 and 5. You can see here. Full load output 1 is 200 divided by 100, 2 megawatt, 2 PU, 500 divided by 100 as 5 PU, 50 divided by 50 as 1 PU. So, base of the system, what the problem has taken is 100 megawatt and 50 Hertz. Now I have this 4% group means if I have 1 on the y-axis, 1, 1.01, 1.02, 1.03, 1.04, like that, for the fractions, I can scale along the y-axis. And along the x-axis, it is 2, 5, like that, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. 0.5 PU each. The power increment, frequency increment, power increment, I just keep ready. Then to generate the requirement, what I should do for the first machine, it is 200 megawatt, means 2 PU. Observe the 2 PU mark here. 2 PU mark, you join with the 1.04. It's a 4% group characteristic. 4% means 1 PU, 0.04 from this. 1.04 point, you just circle a dot here. This dot for the first machine, 2 PU, you join this to the x-axis here. This is the first curve you can develop. 2 PU, 1.04 PU frequency. Then second machine is 5 PU, 1.04 frequency. Draw another wider line to 5. So you have done plot of frequency and power related to this problem. It is 200 megawatt converted to 2 PU, 500 megawatt converted to 5 PU, and frequency 50 Hertz became 1 PU, and you converted 0.04 of that as 1.04 PU. From 1.04 PU, you joined 2 on the x-axis. From 1.04 PU, you joined it to 5 as a power unit. This made your first arrangement. Then, let us say, at some point, just draw a horizontal line, roughly a horizontal. You can see this dotted line being drawn by the presentation here. Dot, 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 dot. Be the point of parallel operation at certain frequency F1. F1 being a point of frequency where X megawatt is shared by machine 1, certain value graphically X megawatt, and 4 minus X. This 400 megawatt is connected to 400 divided by 100. It becomes 4. 4 PU minus X. So X PU is shared by machine 1. 4 minus X PU is shared by machine 2 at a frequency F1 PU. F1 PU is the expected operating frequency for 4 PU load. That is called a dotted line intersecting line 1, line 2 at point X. What is the X megawatt? At 4 minus X, what is the megawatt? I have to calculate. This is how, like regular, what I did here, X and PL minus X. And what is this Y? I am just making it as the point of F1 here. 1.04 minus F1, nothing but Y for me. The same way, I have F1 point, 1.04 here, and X, 4 minus X here. Now, what is my question? Very similar. Start taking the ratios. The ratio of, just see here, delta F by X. delta f by 4 minus x equal to what? Just I'll go back here, this point. What is this? Delta f by x, frequency deviation experienced by machine 1, experienced machine 2. These two small triangle you imagine here, a triangle with the red hypotenuse. I'm just making a path here. A triangle with the blue hypotenuse. They share common side y. Y is the common side. That is the reason I am going to write this ratios. The same way, here I have 1.04 and f1. This is the length of side common for triangle number 1 here. Just see my triangle which I am marking here. And triangle number 2 here, wider one. Hope this is able to be viewed by you carefully. Wider triangle. For this 1.04 to f1, this side is common. Then I can write delta f, which is the vertical axis, divided by share of first machine. Delta f is the common deviation divided by share of first machine equal to droop of first machine divided by capacity of first machine. I come back. What is the capacity of first machine? 2. What is the droop of that? 0.04, 4%. Where is that 4%? Here, 4%. It means delta f by x equal to 0.04 divided by 2. Similarly, delta f by share of second machine, 4 minus x equal to droop of second machine, capacity of second machine. Second machine being 5 pu. So you can see. Now you got two equations. When I take a ratio of them, delta f cancel. Nothing but y in the previous problem. Y got cancelled here when I take a ratio. Same way, when I take a ratio, I'll be able to get the value of x from this. You can see, x works out as 114.285 megawatts. So these are really interesting problems, but we have to be very engineering in applying the things. So therefore, you should be cautious to think this ratio of particular two generator. Delta f by x, it's the droop divided by capacity. Delta f by share of other machine equal to its droop divided by its capacity. When I take a ratio, unknown x can be found out. X makes your first load of generator. 114.285 megawatt is the share of first unit. Then if you want to get the second machine, what is being done? It's very simple. You know that 400 megawatt is the total demand. 400 minus 114. It's being done here in the bottom. 285.715. 285.715 is the loading of second generator. 114.285 is the loading from first machine. If I add them, it should lead to me 400. Then, what is that frequency deviation? From 1.04, when there were no load, suddenly loaded, dip in frequency has come to f1. What is the point f1? Is it safe above this or not? I would like to see. f1 I want to calculate. Nothing but delta f, this vertical side I want to calculate. To calculate that, what I will do? I will use one of the equation. Either this or this. I use it here. Delta f equal to 0.04 divided by 2 into x. X I put over here. When I do it, it becomes 0.02 into x, because this 2 and 0.04 is cancelled. 0.02 into x, it stands as 0.022857 pu. This is the drop in frequency in the per unit scale. Then what is in new frequency from standing point? f1 equal to 1.04 minus the value dropped, 0.022857. It stands here as 1.017428. Let us take 3 digits. 1.017 pu. It is the per unit notation into 50. If I do, it becomes 50.87. Now I am getting. It's very safe. These two generators sharing a load of 400 megawatt, being 4% in group regulation, they are able to cope up this load at 50.875 hertz of frequency. Frequency is very well safe. So therefore, drop in frequency from the base 1.04 has come to 50.857. This is how the group natures of generators being understood by graphical mode. So I just gone very simple. Read the problem to you, made you people to understand how few workout is being done in this problem. How a plot can be done very simple by sketches. How assumed ratios of x and load minus x can be understood for delta f deviation, and I can take a ratio. Ratio can be ratio with equation to lead your answer 1 and 2. This is how my first problem, second problem, third problem, fourth problem might have made you convenient to understand